of you have already connected. Let me share my screen. Get hold of it. Okay, share. I hope you can see it. Okay, so let me put the chat window on top. Okay, so if you will have a question, let me know, or just tell me aloud, because sometimes I just miss what you type in the chat box. All right, so today we will start new topic. Luckily, we have finished design patterns a week ago, so it took 2 lectures to go through all the patterns. There were a lot, but this basically concludes the second task alone, because until here we had all the topics covered which are needed for the second task, first and second task, to complete the homework. Okay, so basically this is the swim line where we can put first and second task. So 2/3 are over. So that's good. So basically, I can see that for the task 1, I have received 20 projects. 3 projects are still pending. I think one of them we have solved yesterday with Paulus. So I still need to fix one of these. So 2 of them will be still hanging around. So if you have received a message from me telling that something is wrong and you still have 0 on your task evaluation, so you need to take some action. As well, if you haven't completed anything at all, so you still, if you want to be allowed for the exam, you have to finish task 1. This is by the rules, by the Bible. Is required, right? So mandatory for exam. So task 1 is mandatory to be allowed to exam. I'm reminding you, and you can still do that. This is not a problem, but project will not score any point. But anyway, this is required for the task. So task 2. In task 2, you have already submitted a few projects. 2 of them, 5 in total. 2 of them I still need to evaluate. So okay, I will do this sometime soon. And this project mostly about the design patterns. So you have to implement a few design patterns to make it work and things like that. Okay, so now lecture number 7, 8, and 9. This is mostly about the task 3. Deadlines for task 2 and task 3 are actually not set, so you can submit until the end of semester. So basically, May is the deadline, right at the end. Okay, so for task 3, I have 1 which need to be evaluated. Okay, somebody has submitted one task already for the third homework. So it's nice, it's okay. So basically we will start. I just thought that we would rather start from the persistence, but that's okay. Let's go as it is set up here. So we will have a couple of lectures for the concurrency, then 1 lecture for persistence, and 1 or 2 lectures for functional programming. We will see. All right, so this is regarding the general organization and the status. So if you have any questions, you can post them now. If not, I think that everybody is happy about how it is going on so far. So basically, we can move on. Let me see. Okay, most of you have connected already. Good. So basically, we can start the lecture. So we will go through a bunch of examples. I will show you around how the basic concurrency programming is being made in Java. And I guess the next week, the week after, we will look into the advanced topics, into the algorithms which are more advanced in Java. Okay, so basically concurrency or parallel programming is a must to know for the good developer, right? So basically we have all the overall topics in this session is split into two parts. So basics and the special package, which was put in Java 8, if I remember correctly. This is Java Util Concurrent, where lots of objects and algorithms are made to help in order to program more efficiently in the parallel world. So basically, today we will look into the basics. So this include the process builder, thread, and synchronization. Okay, so basically multi-threaded applications are very much common these days in any environment which you would encounter as a programmer, because actually this is the only way since the beginning of the century, actually, we can reach a higher throughput for the applications, because the performance of the CPUs has stopped evolving due to the bottlenecks of the silicon-based processors, and we are not increasing that much. So that's why the designers of the CPUs started to develop to include multiple thread support, multiple CPUs, multiple cores, as they called, into the processor itself. So basically, programmers has to adapt. So they have to parallelize their programs in order to gain the performance boost and to make the higher throughput for their applications. That's why we see the increase. It's already a while, it's already a couple of decades, where we see the increase of these techniques that leverage the usage of these multi-threaded environments, like the multi-core processors, multiple CPU systems, and things like that. So that's why we have a bunch of various things which are included into Java in order to use multi-threaded capabilities of the CPU and operating system. So basically here is just a simple dummy example where the multi-threaded processing of some orders in the web application, right? Okay, so this is something like a online shop, which receives a request to sell something, right? So basically, at first it does the consistency check. So the request goes into the application, it does the consistency check. This is something like a queue right here, right? So then it goes to the credit check, stock check, and the confirmation of the order, right? And then it reaches order database. So along with this main thread of the checkups and order completion, right? Order assessment, it basically has the branch which does on a side the fraud check. So this basically thing is a consequent, right? Is a sequence of actions that need to be taken, and it is dependent on the other, right? At first you need to check the consistency, then you check the credit, and after you check the stock. But fraud check, actually, if it is a true order not, can be done on a side. So that's why we can basically split the execution, do this on one thread, on one CPU, as you can imagine, or on one computer, right? And this can be done on a separate computer. And once we will formulate the final order, we basically receive output from one chain of executions and from the other. So once we join these results, we basically make the final decision if the order is okay or not. So if it was okay, we just basically proceed with storing in the database and response. So this kind of situation is very common, and this is just basic situation taken from the book of the well-grounded Java developer. Okay, so basically we will be looking into these multi-threaded cases in Java. So basically, in order to use the multi-process, multi-threaded programming in Java, you have two things on your hands, right? Either you can span a different another process, which is on the operating system level, is just a separate application that executes on the environment, right? So it has all the benefits that come from the operating system, so meaning all the resources, memory isolated, and things like that. So you just basically run as a separate application. Or you have another way of doing that to spawn a thread, a separate thread, which you can consider being a lightweight process. So both process and thread, they both have the same capabilities of execution of your code. But the vital difference is that the process is a very, very costly thing. It comes on from the operating system level. It requires its separate memory, its separate set of all the resources required. Though thread has just a separate set of registers, a pointer, right? And then it basically follows a separate path of execution on the program, but it shares the same memory. So memory as the most expensive resource in both accessing and allocating is actually shared. That's why threads are the lightweight processes. It has lots of benefits, this way of execution as a thread, but it has bad things as well, drawbacks as well. This includes sharing data, right? So we will be talking about this, and most complications about the multi-threaded executions, multi-threaded programs, comes to the synchronization of data access, because data is in a flux. Okay, so basically, let's briefly look into the processes, right? So process is just a separate program that is being executed on the operating system level. And you can do that. I will show you an example how you can actually execute an application from the operating system level in a sequence, but actually not in a sequence, in a parallel. But actually, the point is that this execution is very costly, right? This is a separate process, as well as communication between processes is not so efficient, because you need to create a pipe or a socket. You need to create something like an port, open some port, which will be used for communication between processes, and this is not efficient. This is not efficient. This is okay when you have a separate machines running on the network, right? But when you're running the same application on the same operating system and virtual environment, when basically it is much more efficient to have it separate threads. Okay, so basically for the processes, we have various utilities in Java API, like just process builder, where you, as a builder pattern, right, you can imagine, you just basically provide various parameters. You can omit, you can skip some parameters if which you don't like, but you basically set up environment, working directory, etc., 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 set up whatever is needed, and then press build. Oops, not build, start. Right, and it basically starts the process, it spawns the process, and it's being executed in parallel as a separate instance, right, an operating system. This is just an example where you have the simple process spawned right here, right, the command and with our arguments, and here you just started the process builder. You don't have a process. This is a running process, right, P, and this is PB. This is a process builder. This is not yet a process, but a builder. So then you just basically can assemble environment. These are various variables that will be accessible from the process. Then you can set up various directories, current directories. You can redirect streams, error and output. And once you have set up everything you would need for the parallel application, you basically spawn it by process builder.start. And then you get a handle on a process for the control and access of all the utilities by basically using this p variable. Okay, so since Java API, since Java 9, we have some additional utilities, write process handle, something like this. Then you can get a handle on the currently running process, because you are always, when you're running in Java applications, you're always in the context of some process. So basically, you can get a handle of your currently running process, right? So for instance, get info and things like that. Yeah, so get commands. As you can see, you can spot immediately that there is a pattern of optionals, right? So command dot or else, right? So basically this actually returns the optional. So this pattern of optionals actually indicates that this is something from Java 9. This is not an Asian Java, right? So this is a new Java usage. So it's follow some new patterns like the lambdas here as well, right? They can be rewritten in an Asian style, but this is a new style. So basically, this example is just an indication that this is coming from Java 9+, since Java, at the time when Java have started producing so many versions. Okay, so basically, this is the same business. When you have the process handle, then you can access various information from the currently running process or whatever process that you have handle for. Okay, so this is okay. So basically, runtime, get runtime, execute. You execute and you get the process, and from this process you get extract handle, which is basically access to various information. Okay, so let's go and dive into some example right now. So I will be showing you an example. So example, you have an access to these examples as well. So basically, process demo, this is just a launch of the process. And this process basically executes the find command. It looks up the target folder and lists all the files, right? So process builder, process start, and it starts the guy, right? So basically the guy starts, and this is loops for reading line by line, and once line has finished, you basically get it. All right, so run file. Okay, so basically it runs, it spawns a process, this runs the find command. So this is in sequence execution of the process, but it basically lists the target contents of a target folder, so nothing special in here. Okay, so this is a way to execute the process. And here we have another example, which is basically an illustration how you can run the same Java application from here, from the application. We will be running this application twice in parallel. So basically, as you can see in the beginning, this is the main method, right? So we entering this method, and then we get various information about the currently executed environment. So we basically get the Java home, then we get the handle to the Java program. So we should be able to spawn the new virtual machine. This is a class we are running at, right? So once we are running this in main, we are actually running in process demo 02. So we get a name of this class, right? And this is, yeah, this was the path of all the packages, and this is the main class, right? Okay, so now we check if we have not received any arguments so far, right? If there are no arguments, this is the default run. What we will do, we will create a FIFO object on the operating system level to change data with another process, right? This will be the channel, FIFO channel, first in, first out channel. This is a list where we basically will put some data so other process can read it back, or vice versa. So we will create a FIFO channel, right? So run command is just basically execution of a command, nothing else, right? And once we created our FIFO object, right, we basically will launch another process which will enter the same main method, right? This method will enter here, the same class path, the same main class, right? With arguments. These are the arguments, right? And so it will be running in parallel. And what after we launch that guy, right, with parallel process, we will be just listening for whatever will be provided into the FIFO channel, into the channel, right? So we will be listening, and this basically will block for each item. It will be reading the line by line. This is a buffered reader. So buffered reader reads line by line the source, and the source is the FIFO channel. It will be reading infinite loop, right? This is do while. Oh, this is not infinite. It will be reading line by line until exit is met, right? Until exit actually is met as one line. Okay, so this is the one program that will be executing by default, right? The other program, which will be spawning here, right? It will pass, it will not enter into this block because arguments will be provided. It will enter this block, right? So what it will do, it will write, it will get the buffered writer into the same FIFO, right, channel, and it will be writing all the arguments we just provided, right? Hello from another process, right? It will be writing these arguments one by one, and at the end, once we finished, it will say exit, right? So basically, this is two processes. One process is this guy, another process is this guy, will be communicating. Okay, so hello from another process. Let's put some additional guy like Java process, right? Or let's put it more specifically, JVM, Java Virtual Machine Process. Okay, so basically now let's try to execute it. Okay, run file. FIFO was not found, blah, blah, blah. Okay, I think I need to run it twice, right? This is some problem because commands FIFO was not created in the beginning. Okay, so now it basically says hello from another JVM process and exit, right? It just told me hello from the other process and exit. Right, so this basically told what it received from that guy, and this guy was actually writing in the previous one. Okay, so this is just an example how you can use the process as a parallelization for your programs. And that's it about the processes, because this is not actually how it's being used in most ways in order to parallelize the programs. In most cases, this is actually about the threads. All right, so threads are actually execution points, right? And each process has at least one thread, right? This is a pointer in the program that runs a separate sequence of instructions, and each and every process has at least one thread, and this thread is called a main thread, right? Main thread. This is where we have this main function, main method is coming from. So once you launch the process, it basically acquires all the required resources and starts the main thread, which enters main function, right? Main method in the specified class. Okay. So each application has at least one thread or several. You can actually count, and this basically makes all the signal management, handling, and so on, memory management things to work out. And this everything is built in as a multi-threaded specification of Java platform. Okay, so what comes for Java threading model? It says that the data objects and data is actually shared, visible by default, and has a mutable state. So this is basically the biggest challenge that access to data from different threads is not controlled, mostly by default, right? And you're basically accessing various data items, reading data, writing data, all altering data, right? And this happens in parallel. So here you get a bunch of problems with the synchronization, which you need to handle by hand, because Java does not do this for you. You need to specifically or explicitly tell what you want, how to you want to manage. Okay, so the scheduling is actually preemptive. It means that which thread is actually executing. When we have less cores than we have threads, and this actually happens quite often, then threads are being stopped and executed by force. And this is decided by the scheduling mechanism, and this is not up for the thread, right? What threads can declare? Threads can declare their state, like, for instance, go into sleep mode, look for the resource, etc. We will look into various states of the threads, but actually, and they can state, each thread can state their priority. But for instance, I'm of a high priority, so please be gentle to me and give me as much CPU as you can. But that's it. What threads can do for the scheduler. Okay, so again, objects can easily be shared between all threads. Objects can be changed or mutated by any thread. So these are things I already told. The thread scheduler can swap threads on, of course, at any time. So again, by force, methods must be able to be swapped out while they are running. Must be able to swap out while they run. Okay, so basically, yeah. Objects can be locked to protect vulnerable data. Yeah, so basically, if you want to control the access to the data, this is where the locking comes in. But we will talk about this later on. At first, we need to understand the mechanics, how actually execution of the separate threads happening. Okay, so basically, after a while, so this was already from day one of Java. But then it was introduced the new package Java Util Concurrent, which was developed in order to solve various issues, which usually happening with the programming in multi-threaded environment. This concerns safety, liveness, performance, and reusability, because again, we have various patterns, right, in multi-threaded environment programming. Okay, so basically we have a couple of objects, and one of them is main and associated with the thread itself. So this is a thread class coming from deep down below with JVM. This is Java Lang thread. And thread actually is an execution of a program within the process, right? So JVM allows an application to have multiple threads. Yes, this was told. Thread has a priority, etc. So basically, we have a special class which is associated with a running thread, right? So basically, you can access information about the current program which you are looking at a certain time, and you have to access to all the information via thread class. All right. So basically, each thread has a state. So these are the states, state diagram for the Java threads. So basically, once you start with the thread, right, it is ready to run. And once the scheduler has chosen this thread, it's actually gets an running state, executing state. If the thread says, I want to go to sleep, so basically sleep at a certain amount of time, it gets into the sleeping state. And once it's off, it goes into the ready to run and most probably running again. So basically all the locks regarding the blocking on the data access happening through waiting state, right? Thread wait. And once it is waiting for the object to actually to get an access on a data item, in order to wake up, it has to be notified. And this is a notification mechanism. I will talk about this later on, but this is basically waiting on a lock, right? So basically control of data accesses are happening with locks. And basically each thread can get into the waiting state for the certain data item, right? Once it got off the lock, so basically it notified, it gets into the ready to run and possibly running again. As well, threads can go into the blocked state, right? So they can be blocked by looking into some specific for the specific access into the IO, for instance, reading file, or saying blocked on sync. Okay, so basically they're getting blocked, and on blocks they actually stop, just like they stop here on a waiting side, right? And after they have received data, we basically get into running again. Okay, another friend can close the socket. So basically socket is closed, so it goes and dies. And once execution is done, basically reach the end of a program, it goes into the dead state, right? Like a finished state. Okay, so basically a thread basically can be spawned, can be created in a way that you basically have a separate class which extends thread, right? And so basically this thread becomes a superclass, and you have to implement run method, right? Override run method. And this run method is your program which you want to execute in parallel, right? This is an entry point for your program. So just like this, for instance, I have declared my runner thread, right? So I have it like this. The new instance of this thread, and p.start. This basically spawns a parallel execution of the program. And entry point is here, right? So run method, you just send a point for the execution. There is an alternative. Alternative is to have the runnable interface, right? So runnable interface. This is interface, which I create a new class to implement this runnable. And this is, again, we have a run. Right here we had run, and here we have run as well. So basically you have this runnable, a separate guy, and now you can basically put it into the thread, again the new thread, put runner and start it. So these two ways of executing a new program in parallel actually were in Java from day one. This is the classical way, basics. The new way is to use various callables and so on. There are very many new ways, future pattern, etc., which we will talk about later on, actually next week. But these are the classical ways how to do that. Okay, so threads basically can go into the groups, so you can have a handle to control multiple threads with one go. For instance, to interrupt them, to count them, to get a number of threads in a certain state, and so on. So basically, threads can be grouped. You can get access to the current thread, for instance, thread.currentThread. And once you do that, you can print about the thread information, right? So once you're running in some thread, you basically can reach from this static method information about the thread, right? So as well, if you have spawned the thread, like here, right, you have executed the new thread. So basically you can, of course, you can reach this information as well. So basically threads are self-descriptive. They describe information about themselves, right? Okay, so sleep basically goes sleep for a certain time, right? So you can basically sleep for that number of milliseconds, right? So for 4 seconds, you basically 4,000. There are new ways to sleep, maybe new modern ways, but this is a classical, right? Thread.sleep. So basically, you put the current thread into the sleep. This is, again, static method, as you can see. Okay, so basically the interrupt, in order to communicate with the thread, so you can send an interrupt, you can send this multiple times. And basically once interrupted, for instance, if thread has went into the sleep state, right, like here, 4,000 in the example, right, and you send from other thread, from other program .interrupt to that thread, right, it will jump off the sleep state and go here, right? And basically will go into this exception block, right? Interrupted exception. And this, if you are calling methods like sleep and so on, like wait, you have to be prepared and to check for interrupted exception to handle it. Okay, so basically, if you are not doing that, you can check. You can check if the thread was interrupted or not. Right, so basically, if you have nothing, if you have an infinite loop running here, so you can basically all the time check if the thread was interrupted or not, right, in order to handle something when another thread actually sends you interrupt. Okay, so once you have multiple threads running, right, once you have multiple threads running, you can actually, what you can actually do, you can wait for the thread to finish by calling tjoin. What it does, it will stop here, the current thread will stop here and wait for the T thread to finish its execution right here, right? So basically join is the way to wait for the T thread to finish. Okay, so this was the mechanics of the functions, how to actually execute the various threads. So now let's go and take a look into the examples. Okay, no questions so far. Okay, so I have various examples. So most of the examples will be showing prime calculations. Right, prime numbers calculation. So basically we have a function, static one, which checks for the number being a prime number or not. How it is being done, it goes from 2 until the number, right, and tries to see if it's actually divisible by this C number, right? And if it is, right, its model is equals to 0, it basically returns false because this is not a prime number. Right. Otherwise, if it loops and everything is fine, it says that it's true. The provided n argument is the prime number. Okay, so this is the thread that we have. It requires in the required arguments constructor from and to. This is the interval that we should be looking for with prime numbers. And as well, it provides from above the set where we have to put in instructions, right? So this is the thread. This is the thread, prime thread, right? Which has the mandatory run method, right? And in this run method, we just basically loop from to, right? And we'll be checking if it is a prime or not. And if it is a prime number, we would just basically add it to the set of results. Okay, so this is simple execution from to and checking if it's a prime number or not. So basically from this provided interval, we're collecting all the prime numbers. That's the job. Okay, so this is basically our main program. We have a bunch of blocks for various examples. And we just basically, what we do, we create a set for the results where we want to store results. And what we do, we synchronize this set, remember, again, so this is the decorator, which basically has another guy inside, the tree set. And what it does, it synchronizes all the modifying methods, right? Okay, so this result set is ready for the multi-threaded environment. We will be talking about this later on, but already I have mentioned a little bit about this. Okay, so basically here we have a thread, which we call a single variable from 1 to 300 thousandths, right? And here we will be storing results. And we want to measure the time of execution. So basically we will take nano time in nanoseconds, right? We will hit run. As you can see, we do not spawn it. We don't do start. We just execute run. So we just execute this method directly. This means that we will be running this in the main thread. This is in sequence. This is not parallel, this is execution in sequence, right? So we hit run, and what we do at the end, once it's finished, we just basically calculate the time difference, right? The time difference, so we want to know how many seconds this actually happened. We use the converter. Okay, so after doing so, after calculating from 1 to 300,000 a sequence, we will do the same trick, but this time we will have two threads, one thread, another thread, one from 1 to 150,000, another from 150,000 to 300,000. So basically the same job, but divided into the two pieces, right? So this time, these threads will be started as normal thing, right? And then after starting them in sequence, right, the main thread stop here and will wait for the first one and the second one to stop their execution, right? So these guys will be running in parallel, and here we just wait for them to finish. So once we finished, we will again measure the time. How much time does it lapse, right? Here's the same trick, but we will have 3 threads, right? So again, from 100,000 to 200, and again, so the job is divided into 3 pieces. Here we have 6 pieces, right, with smaller chunks. And here, I don't know how many, 10 pieces, right? So again, so this is just an example how this can be done, okay? So let's run this guy, run file, and we'll see the output. Right, so it executes. Should wait a little bit, right, because this is the longest one, I guess. Currently executing. Okay, it took 12 seconds to find 25, almost 26,000 of primes in the range, right? So 2 threads, 9 seconds, 3 threads, 8 seconds. 6 threads, 7 seconds. And 10 threads, 6 seconds. Okay, so it's with this setup, it's twice faster with 10 threads than with 1 thread, right? So the gain is 2 times, right, faster. Of course, this setup, this program is not very well programmed and not very nicely done because it has the bottleneck, right? And one bottleneck, and this bottleneck is actually synchronized collection. So even though the lookup for the prime number is going on in parallel, but writing it into the collection is actually blocking, right? So actually these guys are blocked in this side. So much better would be to accumulate those results in a local set and return it, and then do the aggregation somewhere here, right? So this would be basically a better implementation and fast implementation, I guess, and the gain would be much better. Because now all the 10 threads are actually trying to put numbers into this synchronized sorted set. Okay, so again, on the fly, I can show you how optimizations can be made. Okay, so this was one way of doing that. Another way of doing this is actually to have runnables, right? So prime runner runnable. So this is exactly the same implementation as we saw before. And this is basically prime runner, again, the runnable. So we basically hit run. This is exactly the same implementation, right? So along here, we have these runnables and we have threads, right? And we put these into the threads. So the difference is that you can basically reuse the runnable for the different objects if you have the same configuration. But right here, we have different configurations. That's why we need separate objects for each prime runner. Okay, so basically 3 again and more again. Okay, so since this is basically the same setup, but anyways, let's run and see if results have changed or not. Okay, so probably results will be slightly different, but should follow the same logics. something around 12 seconds should be running the first chunk. Yep, 12 seconds, good. Right, the same prime numbers found, obviously, right? Okay, 9 seconds for 2 threads. Not so much gain, but anyways, there's a little bit. 8 seconds, right, for 3 threads. 7, 4, 6. I think it's the same exactly results. Okay. Yeah, so basically, since we're occupying, this machine is 4-thread machine, 4-core machine, right, CPU. So basically, the gain is up to 4, should be, in the normal execution without this locking guy, right, which we have right here. So basically, more threads addition should not gain so many benefit after all, right? So around 4 should be the maximum gain which we get. And obviously, these threads, since they occupy all the cores available on this machine, would be occupying, right? They are in concurrent environment with the operating system and other processes running on this machine. So that's why basically these results can fluctuate if you measure time. Okay, so let's see what we have here. We have again prime calculations. Oh, these threads now are being put into thread group, right? So again, remember there was a slide about the thread group. So basically we have TG, which is a thread group. So once we initialize these objects, these are put into the thread groups, right? So basically we start them, and what we do, we just have some handle of control. We interrupt, right? We basically interrupt these threads, and now we call them join, right? We wait them for finish. Okay, so let's take a look. Prime runner. Okay, thread demo. I just wanted to see the implementation. Okay, prime runner, where is the implementation? Okay, so basically prime runner is constructed so, the run method is constructed so that it waits for it to be interrupted. You see, nothing here is requires the to handle the interrupted exceptions. So because we don't sleep, we don't wait, we don't do anything, right? We don't block on anything. So here we need to explicitly check for the interruptions. So that's why in this loop we check if the thread was interrupted or not. If it was, we just basically break, right? We exit the thread. This is what I was looking for. Because once you have started in this thread group, all the threads you have started, you basically, they are running, right? They are running. And when you issue interrupt, they one by one, they will stop execution, right? Because we will exit the loop. And then we will basically check how many primes we were able to find. Okay, so let's start and run it, and we'll see how what happens. Okay, so active count 6, active count 6, we said, yeah, it was saying so after the start. How many actives? Were 6, all 6 are running, so 6 threads in 28 milliseconds, so basically 28 milliseconds, they were able to find 778 primes, right? All 6, so running again. Just to say, okay, now in 46 seconds we were able to find 1111. Nice number, right? Okay, so basically interruption just was able to stop all the threads which were included into this thread group. Okay, number 4, example number 4, we just print info about the thread, right? So basically all the info about the thread is being printed here. So basically it says all the information about the thread, just an example, right? Like this, this was in state runnable, so this was a main thread, so it was in state runnable. It has a name, it has an ID, it has a name, priority, right? The group name, if in any, right? Alive, it's a daemon or not, so we will be talking about this later on. So there was another thread which was in state new. So basically it was, I guess, just, yeah, it was just initialized, right? It was not running, so it was in state new, not yet launched. Then another one, then it was already running, right? So it basically has been launched, like here. Okay, and interrupted, it basically said that it's interrupted true. Okay, so basically these are various examples for the thread info. Okay, this is an example of the daemons, right? So let's talk it over a little bit. So basically, here we have a main thread. Main thread is running, right, this application, right? And what we launch another thread, right? And this is another thread. When we just sleep for a while, and then we say, okay, main thread exit here, right? And once the main thread has finished its execution, what is actually happening with these other threads, right? So for instance, this other thread, that one, let's say the daemon false by default, right? It is false by default. So it will be running forever. As you can see, this is infinite loop, and it just sleeps for 2 seconds, right? And then prints, I'm alive, I'm alive, I'm alive, right? And this thread finishes after the 5 seconds, right? So this should print 2, I'm alive, right? It will print 2 hi from blah, blah, right? And then this guy just finished. So what will happen with this running thread? Let's take a look. Okay, we're running the file. And we're running the file. Hi from the user, hi from the user, hi from the user. Main thread finished, right? It just said that I'm bye-bye, I'm going away. But it's still running. The program is still running. And that's the trick, because this thread is the user thread. It's not the daemon thread, right? It's not the utility thread that does something in the background. It is considered as the user thread, so it blocks the end of the program execution, right? So we need to finish it up. How to finish it? Okay, like this. Stop the execution, right? So I killed it. So now let's make this thread a daemon thread, like this. Let's make it a daemon thread, and when we run the file, it starts with daemon thread. Hello, I'm from daemon, right? Hello, hello. And main thread ends, it kills, the application kills automatically all the daemon threads, as you can see, yeah? So if the thread is marked, if the child thread is marked as a daemon, right? Daemon thread, it is automatically killed once the main guy finishes. This is the idea. So daemon threads are considered to be an utility services for services which are not to be waited at the end of the program, right? So this is the difference. So you need to take this into account and to remember the difference. Okay, so this is the simple example of a sleep, right? So we have a loop. We loop over all the items here, and we sleep one by one, right? We sleep for 1 second. Sleep, 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 go, right? Sleep. So this is usually used when you want to wait for something happening, or you want to just illustrate how threads are working, right? Okay, so this is basically an example for the interruptions. Okay, let me see. Okay, so basically in the main program, we will start a thread, right? Interrupt demo. We will launch it. The main program will sleep for 3 seconds, right? And we'll send interrupt. And it will sleep for 1 second and will send an interrupt, right? So basically after launching the thread, it will send interrupt signal twice. for the interrupt thread, right? And what does this guy will do, right? What it will do. So it will basically will run an infinite loop, right? And will try to sleep each second. It will be sleeping each second. Since it is sleeping, it has to have the interrupt exception handled, all right? So basically, it handles this interrupt exception. And once exception happens, it should jump off this loop and go into this block, right? And so interrupted. So after this block, we will check if this thread is still interrupted or not, right? If it is interrupted or not, right? So we will check that. After this, we will go into this loop for the 100 million of iterations, and we will be running it many times, but we will be checking for it is interrupted or not manually, right? This is checkup manually. And we will check if it is still interrupted or not, right? So this is a trick. Let's try running it. Okay, so it's running, interrupted, and again. Okay, so let's look into this. So basically, we were running and sleeping each second, right? And once we send it interrupted, this actually is printed from this block, right? 01 block. And once we got off the interrupted exception, it is not anymore interrupted, right? So basically, the trick is that handling interrupted exception in the block clears out interrupted flag, right? Interrupted flag was cleared out. Now we did this the same trick manually, right? So running again. We handled this interruption manually, right? Here, 02 interrupted. But once we got off there, it is still in the interrupted state, as you can see, still interrupted. So the takeaway from this example is the following, that if interruption is handled by Java API and you got into the interruption block, the flag of interruption is actually cleared out. It is not there anymore. And this makes sense because it was taken care by the exception. But if you do this manually, you basically can rely on the flag later on. Okay, so these were mechanics of the launching the thread and working with the thread. So basically sleeps, interruptions, daemons, and things like that. I showed you around. So I basically, these basic things, how to launch a thread, how to execute it, and so on. I think you understood. Okay, let's go back into the slides. Okay, let's take a look where it will lead us. Okay, so basically now we will go into the section, I think, where we will talk about the synchronization. And this is the main topic overall in multi-thread environments. So basically handling and taking care of the data. Yep, so basically it has a shared memory and the data is in flux, always changing, right? Unless it is read-only, thread local, or protected by the lock, right? So things like that. So in order to handle data efficiently, you need to understand this into multi-thread environment. As well, the other option is to actually have immutable objects only. And as you know, immutable objects are considered to be read-only objects. So that's an advantage of having immutable objects. And that's why lots of objects coming from Java API are actually immutable. Okay, so locks are used as a measure to access immutable objects. So we can have a situation of a deadlock. So I have encountered multiple times in my career where we were working on huge applications. And from time to time, we got into a situation of deadlocks. And this is very, very hard to debug, actually. It's quite hard to find them out because they are happening randomly. And to find out what's actually caused the deadlock is very hard to find. As well, we have other bad situation which happens with usage of maybe abuse of the locks is actually the race conditions, where we are updating the accessing variables, and these variables are going through the intermediate caches. And basically, updates and reads from the main memory is actually happening in parallel, and we read some word information, some intermediate information. Okay, so we will look into this as well. So what happens overall with this shared memory thing is that application behavior is non-deterministic, right? And code coverage, usually coverage means that if it's covered with tests or not alone is insufficient in most cases, and threads are racing, and you have an undeterministic situation in what's happening, right? So this is the tricky situation for programming. Okay, so basically everything about the specification is described into the Java memory model, right? So multi-threaded is described over there. If you are interested in how it's actually constructed, you can go into this document, but this is not an easy read. It has the definitions about the synchronizations, volatiles, finals, synchronized, etc., etc. All these three things are actually described over there. Okay, so what we have in order to prevent all these bad things that I just told you about is basically a lock, a mechanism of synchronizing various blocks and data. So in Java, each object acts as a lock. Each object, so in the super type, in the ancestor of all objects, we have all the mechanisms that are required to have a lock, right? So basically, taking each object, we can use it as a locking mechanism, right? So we need to point in which object, which instance exactly is actually should be acting as a lock. So once a thread reaches a certain point of execution, it can call object, so some instance, right, wait, right? So it will block on this point, right? It will wait until somebody else, right, some other thread will call notify, right? So if you have multiple threads accumulated at the point of wait for some objects, right, acting as a lock, and another thread which exits the execution calls the notify, so one of the threads is actually goes off the block and will enter goes off the block and enters the block, right? Okay, notifies all. So all the threads at the wait we basically passes through. Okay, so basically this blocks a thread, this actually unlocks them, right? So one thread is at wait position, another one notifies, so this got off the wait. So usually this can be implemented. I think I will show you an example how this can be implemented with the pure objects, but usually this is not how it's made. Usually we have something like this, where we are using the synchronized keyword, right? So this basically synchronized keyword can be put on the method. So here you can see a method, public void increment, public void decrement. So obviously these methods are the methods that modify the state. So putting these synchronized keywords, they make sure that only one thread actually enters the method. All the others are waiting, right? So basically for this specific lock, this object, right, the current instance, acts as a locking mechanism. This implies that once all the methods, multiple methods are trying to access these, multiple threads are trying to access these methods, they are all blocked and wait until some of the threads actually exits one of the methods and calls notify. Right, so basically this means that this object actually locks all the threads regardless of which method we try to access. So this is one way of blocking. Another way of blocking is actually to use the synchronized keyword on the arbitrary block in the code. But here you have to provide the locking mechanism, right? So the lock, the object has to be provided. So any object would just fit well. So usually this method is in some class. So you put this O as a field in a class, right? This is just an object. And it acts as a lock. So this way you can diversify and block certain pieces of code, one thing, and then you can think of multiple locks, and you can lock on specific things, because locking methods like that is just basically locking them, all of them, with a single lock, and this is not very, very efficient usually. Okay, so this was a synchronized. Another keyword which is used in Java is a volatile keyword, which is basically to avoid these race conditions. And if you mark your variable as being a volatile, they actually, Java virtual machine makes sure that this data is read from the main memory and written back to the main memory while accessing the value, right, or modifying it. Okay, because the thing is that operations on the long variables, like for instance 64-bit data, is not atomic operation, meaning that it has the CPU has to pass a few operations. So basically putting into the buffer, flushing into the memory, putting in the buffer, flushing into memory. So things like that, because the data bus is not long enough, right, to handle all the data in one go. So that's why this can be interrupted in between, and you can get non-consistent results by reading or writing into the data items. So putting volatile makes sure that the data instance, the field, is actually read and written right from memory by passing all these multiple operations. Okay, so this is basically double checking problem, double locking problem, which I already told you about. This is for the singleton. Remember, this was a synchronized block, and you need to check null here and null here, because you need to check null in the synchronized block, because some other thread might have exited it beforehand. You have a solution for that as a holder. It is here. Okay, so there is a notion about the synchronization, that a fully synchronized class is such a class that has all the methods that modify something are actually put to be synchronized, right? Things and all these rules might be are presented here. No public fields and so on. So having class like that actually is a good thing, because it is safe for multi-thread environment. But the drawback is that it is a bottleneck. For any execution in the multi-thread environment, this is a bottleneck. So all the threads, since you're trying to gain lots of efficiency, would be waiting for other threads actually on this class. And some objects, some methods, as it is visible here, for instance, get I, right, does not modify anything. So why to synchronize this method, I just don't know, right? Maybe it's in a flux, it's being modified, but anyway, this might not be a good idea to synchronize getters. Setters, I do agree, but getters might not be a good idea. But anyway, this is a fully synchronized class. It has its way to live, but this is a bottleneck anyway for multi-thread environment program. Okay, so this brings me to the advanced topics, which I will leave for next week. Right now, let's take a look at a few examples, which I have synchronization, or quite a bit of examples, right? Starting from 6, 7, yes. right order. Okay. So I will not take a lot of your time. I basically will run through quickly these examples, and these examples you can look at afterwards by yourself. So basically, this is an example how the arbitrary object, this object, can be used for synchronization, right? So wait, notify all, etc. So this is an example how to use this object for synchronization, right? So things like that. There are some limitations in order to implement this, that this method need to be synchronized. For instance, if I remove this, it would fail to execute, I guess, run file, right? Let me check. Yeah, it does not execute. Illegal monitor exception, yeah. So basically now it should work, I guess. Let's take a look. It's print something. Yeah, so now it works. It waits for something, runs, etc. So basically all the execution, releases, notifications, etc. all is happening over here, right? And this object is used as a mean for synchronizing between 10 threads. 10 threads. Yeah, I think 10 threads, because this is a loop of 10. Okay. So basically you can look after, but this is just an example of how you can do vanilla implementation of the locking mechanism. Okay, so this is another example where we have incrementation. Yeah, we have 10 threads. Yeah, seems to be 10 threads. Yeah, launched 10 threads, and each thread is looping for 10,000 times and increment some value, right? Calling these methods, right? So basically try to increment these values, so 10 threads for 10,000 times. So it should be 1,000,000 in total. These threads are started here and joined here. So we expect that these two variables would be 1,000,000, right? 10 times, no, not 1,000,000, 100,000, right? 100,000, 10 times 10,000. So we expect these two values will be 100,000 both. One of them is synchronized, another one is not, right? Let's try to run it. Okay, so basically synchronized is correct, 100,000. So 10 threads were incrementing for 10,000, right, times variable, and this variable unsynchronized is 99757. So basically something, at some point it just missed synchronization, right? So this is what happens when you have multiple threads accessing the same variable, right, and try to modify it. Because at some point it was not written down into the database, at some point it was in a flux, it was just on a way, etc., etc. So what happened? Many 10 threads were modifying same variable, and it has gone out of scope, right? What we would expect. If we run this again, we should get slightly different result, obviously. So that value is actually undetermined, right? Okay, so that point. So basically the same example, we just put the volatile on top of the variable, right? So basically we have longs now. So longs are volatile, and we check that if this example would be enough for actually handling this uncertain situation. We're running the file. Let's check. So simple count, right, missed a lot, and volatile has missed even more, right? So basically, in my experience, putting volatile is not enough, because we had a slower operation, one thing, right? The operation was slower because it was going into the main memory all the time, one thing. The other thing what happened is that we had simultaneous accesses anyways, right? So basically, were multiple threads reading the same variable simultaneously and writing it down into the main memory. Anyway, so adding volatile keyword just does not help in this example, right? But it slowed it down I think if we would run, we would get consistently slower results because of the accessing to a main memory, right? This time it was higher. Okay, so things happen. Okay, so uncertain situation, as you can see, right? Okay, so this is some kind of an example where we have threads running, 2 threads running. They would be using the separate logs. So this is log 01, log 02. This is, I guess, an example of the deadlock, right? I think this is deadlock. I have suspicion because this is what usually happens. So, okay, we have a thread running run 01, another thread running run 02. Okay, so 01 basically locks on log 01, right? So it holds log 01 and then calls run 2, which would require log 02. And this guy is vice versa. It goes, takes the log 02, and then calls run 01. So this is the deadlock situation, right? We are in one thread, which will hold log 01. Another thread will hold log 02, and then require each other's log access. So this is deadlock situation. This is an example of how the deadlock can happen, right? So basically running it out. Yep, so thread 0 just got log 01, right? Thread 1 got log 02, and now thread 1 waiting for log 01, right? Still holding log 02, and thread 0 waiting for log 02, still holding log 01, right? So this is basically a deadlock. We just have stuck a couple of threads, and we will not move anyhow. So the only possibility is actually to kill them, to kill the application. So this is an obvious situation, but these situations might not be obvious all the time, especially with the big application. Okay, I have experienced this a few times already. This is atomic long. Let me check. I think this goes into the thread local demo, etc. So this goes into the concurrency. Okay, this is for, yeah. So these examples are more advanced ones. This goes for the next section, and I think that at the example number 11. Example number 10, we just stop here for today, because next week we will go into the more advanced topics, slightly more advanced topics right here. And this is half of the presentation still, half of the slides and half of the examples. Okay, so that's it for today. Hopefully you're not asleep. I have to deliver that. Okay, task number 3. What in general need to be done there? Okay, there are no tests as in previous ones. There are tests, so it should be tests. Are they gone anywhere? Okay, let me check. I can explain you this. Okay, I'm going into the repository. Okay, so this is task number 3, right? I hope that some of you already are looking into this. Okay, so basically, oh, maybe I can open it up. Let me check. Maybe I have it over here. Close. Hopefully I will not open the implemented thing right already. Project. Okay, Java samples, tasks. Task 03. Okay. Right. Yep, I have it over here. Okay, it's red a little bit, right? I think this is red because the Java is a little bit higher up. Let me check. No, it's red because of these guys. Why this one is red should not be. Get code. Oh, these are various getters. Let me increment a little bit. I think the Lombok. right? The Lombok is not high enough for this version. Okay, let me put it like this. If you encounter this situation when you just need to increment the Lombok, at least for me it works. Okay, so basically task number 3 is composed of 2 separate tasks, unrelated, right? The first one, let's look into the first one as being an MT task, right? MT, this is multi-threaded task. So multi-threaded task is a task to actually implement the multi-threaded application, which is implemented right now, but is not multi-threaded, right? It is not ready to be executed in multi-threaded environment. So there are tests, as you can see, there are tests, and test number 1 should be working okay. All right, so let's try to run it on my computer. Okay, I will be test file. Not sure if it will work. Yep, so basically what it does, it sends the message, a bunch of messages to the server and receives answers, right? This has a client implemented. So this is a client. It receives a socket address. So this is a client of some server. And it has a bunch of application, a bunch of functions which are being executed, exec, right? And this is the actual execution. We have a socket opened, right? Socket opened, then the message is assembled, then the everything is put into the buffer and written down to the socket. Okay. And after that, basically we expect a response. So based on the request, on the correlation number, we get a certain response. And the idea is that it works for the single thing, but then we go into the task into the test suite number 2. So basically test number 2, it should fail because it launches one client and the other client, and second connection fails, right? It says with second connection fail, must not reach with one. Yeah, must not reach with one. So basically it should reach that point. Now I see the problem here. I need to explain the task number 3 in the better way. So basically I need to draw the scheme, how it works. I need to explain it, and I need to explain it the solution. Okay. So basically for this, I need to prepare to find out the scheme and to remember everything. So basically for explaining MT part of the task 03, let's do this next week. Okay. Because then it will be right on time. I will finish everything multi-threaded related with the theory, and we will get into this part of the task 03. Okay, I guess this is okay for you. Okay, because it needs a more extended explanation. But basically the principle is such that test 01 works, others should not, and you should change the MT classes in such a way that they should work in a multi-threaded environment. And I will give you the full extended explanation about how to do that. So I guess this is okay with you. Okay, then the other part from the task 3 is the GPA part. This is access on the Postgres database, which is established in university. And basically, you have to create a modal classes. This is company, person, product, sale, and subject. Then you have to read back data and so on and so forth. So this is basically a persistence part. And persistence we will be looking at next a week after the next one, right? This is persistence. So basically, let's do it. So next week I will finish concurrency and will explain task-free empty part. Week after, I will explain you persistence in theory and will give a full explanation of the task. Okay, just I don't want to run before the train. Java 8 is okay. Java 8 should be fine. Basically, these objects that I would encounter you to use, all the classes that I would rather suggest, recommend you to use for the task are actually not that difficult. And I think with the Java 8 is really enough for implementing it. So the deadline for all remaining tasks, end of May. Yes, exactly. If you want to get additional points, if you want to score higher up, you have to implement. But this is not required. These tasks are not required because I usually find out that this is very difficult for some of you. I don't want to scare out people from Java for their lifetime. So basically, I think the champions who want to succeed and want to get higher marks, we basically are encouraged to use it, to do it. Deadline end of May. OpenGDK. OpenGDK, yeah, you should try it out. I usually try to avoid OpenGDK because it has some drawbacks. I don't remember right now what are they, but I usually tend to use the Oracle. Because all the production environments are using Oracle, so that's why I'm just sticking with Oracle. But OpenGDK is just fine. But this is a question right in time, right? When we're almost over, we're just 1 month before the end. Okay, our second yeah, so June 1st, yeah, just before the June 1st. This is the deadline. Any more questions? I have my homework to do and you do it well. Any frameworks? So any, like Hibernate. Yes, Hibernate is included. So basically you should be looking into what's provided and not to modify what's provided. So basically POM file, right? So POM file, look into a POM file, and this POM file provides you with the Postgres JDBC driver, of course, because you're accessing Postgres. These are the generic ones. Juice, all right, with Juice for injections, and the Hibernate. Right, Hibernate is there. It's a rather old version, but should be fine for you. If you need to upgrade something, yeah, Entity Manager as well. So basically for the GPA, you have everything, all 3 libraries included, should not be using anything else, right, for the task. Any more questions? Okay, thank you, that's good. Yeah, so I guess we just started the multi-threaded thing. I think you've got some ideas about the basics. So next week we will talk over the more advanced things, and I will explain you the task number 3. And most of you have still got to complete the task 02. It is not required. If you are more willing to tackle with the task 3 and don't have so many time for the task 2, you can skip that. Not a problem. This is not a sequential work. These two go in separate thing, right? And another thing is that task 3 is actually of two separate tasks, right? Composed of two items, GPA or persistence and empty. So basically, usually guys tend to implement one of them, and this is okay. Then you will score 1 point. And one of them is easier to implement. Well, it depends. It depends, actually. It depends on what strategy you will take. Okay. So if no more questions, then thanks for your attention and talk to you next week. Bye-bye.